Hi, how's it going? In this video I'm going to talk about radians. Why do we use radians in trigonometry? Why are radians the preferred angle of measure? Okay, this diagram is something that I love. It's showing the relationship between trigonometry and the unit circle. Okay, I really do like this. In particular, this is this sine graph. How is that happening? Why is that happening? It's because we use radians. I'll get onto that very shortly. Okay, this is a unit circle. Okay, what I've done is I've marked off a point that lies in the circle there. Okay, now that point I'm going to call P. Now if that was plotted an XY plane with that as the origin and that's the x-axis, that's the y-axis, you would often say that the coordinates of that point P are coordinates xy. Okay, but we can define them another way. We can define another way using trigonometry. If we drop a perpendicular down to the horizontal axis and look at this right angle triangle, this here, angle theta, that's a really important angle. That's the angle subtended between the positive axis, often called the x-axis, and this radius here from the point O to the point P. Okay, that's angle theta. The radius is 1 of the circle, so the hypotenuse is 1. Now using simple trigonometry, cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. You can see that bit there, the adjacent side marked in green, that's the same as cosine of that angle, cosine theta. And this here, the opposite to that angle theta, that is just sine theta. So we can say that the horizontal component, or sometimes the x-coordinate, is cosine theta, and the vertical component is the y-coordinate. Now I'm talking about distances here, aren't I? And that's where radians come in. Okay. So this here is an arc length. If you think about the whole circle, we talk about a circumference of a circle for a complete circle. The formula for the circumference of a circle is 2 pi r, 2 times pi times the radius. Where the radius of 1, that whole length is going to be 2 pi. Okay, I'm talking about length now, of course, 2 pi. So a quarter of the way around the circle, that's going to be pi over 2. Half of the way around the circle, that's going to be pi. 3 quarters, 3 pi over 2, and 1 full turn, that's going to be 2 pi as a distance. Now, what's radians about? Radians is the notion of what if that angle there was exactly the same as that length there. In other words, we're equating the angle subtended here to the arc length of it. Okay, that's what radians are. That's the definition of a radian. I'll put it in blue for extra emphasis. Let me read it out to you. 1 radian is the angle subtended, created by a sector of a circle, centre the origin, with arc length equal to the radius. That's what 1 radian actually is, okay? So in other words, that is why this here as an angle, we call it pi over 2. Okay, the 90 degrees perpendicular lines, we call it pi over 2 because that is equal to the distance. That's 1/4 of a turn. And that's why 1/2 of a turn, or this straight line here, 180 degrees, that's why it's pi radians from here to here. And that's why a complete turn is 2 pi radians. That's why 360 degrees is equal to 2 pi radians. Okay. Now, let's have a look at that video again. This is drawing the graph of y equals sine theta. This is why the graph sine theta looks like this. Okay. Can you see what's happening? As the point has been traced all the way around the circle, the angle that is being created from the positive x-axis is being plotted along the horizontal scale. Okay. It's being plotted along the horizontal scale. Now I'm going to show you the video again. Don't panic. And watch as it goes all the way around the circle in the angles. So here, pi over 2, that's pi over 2, you see. Or when it comes down to here, that would be pi, which is about 3.141, so it's going to be about there, isn't it? And then it keeps on going, okay? Meanwhile, the height has been plotted out as well. So what you see is the angle as it goes around the circle, and then the height relative to the axis, okay? And that's plotted in radians, and that's why that graph is so nice, okay? Just imagine if it was not plotted that way, if it was plotted with 360 degrees instead. Now I talked about a unit circle. How do I plot a unit circle? It's going to be something like that. You can't even see it, okay? It's going to be something like, it's not really easy to see, is it? Okay? And that's one reason why radians are preferred. If you try to do exactly the same thing with a unit circle, look at the scale. I mean, just from there to there is 50 units. That is 10 units, okay? Try to do it in a unit circle, you cannot plot it nicely on that particular graph. Okay, so let's just go back to that one more time. Okay, this is why we use radians, because it shows that closer link between trigonometry and the unit circle. I do love this video, so I'm going to watch it play out again. There's 3 pi, sorry, there's pi, there's going to be 3 pi over 2 when it gets to it, and it's going to be 2 pi again. Okay, and that's the graph of y equals sine x or y equals sine theta. Okay, moving on. Okay, when the angle is very small. Okay, so look, on this here we've got a very small angle. You can see the arc length is very small as well. Okay, now as you probably can't see this, but as these two are very, very small, okay, the arc length, let me exaggerate, the arc length there is very similar to the straight line distance. Okay, the arc length is similar to the straight line distance. Okay, or in other words, in terms of that angle there, that angle, if it is actually the arc length, they're very, very similar. They're very approximate. Okay. Here, I've shown it a bit bigger here. That's the opposite length there, the sine theta. The straight line bit, that's the arc length. You can see that bit there is very, very similar to this, and then hence this. So we say for small angles in radians, sine theta is approximately equal to theta. You may have seen that somewhere before, okay, or if not, you might see it again sometime. Okay, that's what's called the small angle approximation. Okay, there's an even better approximation if you've done Maclaurin series, you've done the Maclaurin expansion of sine theta. There's an even more accurate approximation to it, but as a very rough estimate for smaller, we're dealing with very small numbers here. Okay. 0.1, for example, is a small value. If you do it in a calculator, do sine of 0.1 in radians, that's approximately the same as 0.1 itself. It's a really good approximation. That only works when you're using radians, it does not work when you're using degrees. Okay, so that's a very handy thing to have. Let's talk about gradients, because at some point it'll be differentiating, or maybe you've differentiated already and you're just watching this to see exactly what we mean by radians and what why we're using radians. Okay, so I've just got the graph here, y equals sine x. I prefer x to theta, do you? I prefer x to theta, to be honest. I've got the graph of y equals sine x in radians, of course, so you can see there, pi over 2 maximum point, pi, and then 2 pi there. And I've also drawn the line y equals x. Okay, can you see when you look at the origin there, the line y equals x is a tangent to the graph y equals sine x at the origin. Okay, and that informs us what the gradient actually is. Okay, that informs what the gradient actually is. Because the gradient of y equals x is just 1, and because that line acts as a tangent to the sine graph at the origin, you can see visually that the gradient is also 1 as well. Now, if you've done some differentiation, you should know that when you differentiate sine x with respect to x, you get cosine of x. Okay? And that tells you what the gradient actually is at any particular point. So when you substitute x equals 0 to find the gradient, cosine of 0 is 1. Okay, that's whether you use radians or degrees, incidentally. Cosine 0 is 1, hence the gradient is 1. That informs us that the derivative of sine x must be cosine x, because it's working, essentially, because we can see that the gradient is 1, and because we've got cosine 0 is equal to 1, that should actually work. Okay. Fundamentally, that's why when we differentiate sine x, you get cosine x. Okay, this result only works when you're dealing with radians. Okay, if we do with degrees, I showed you this graph earlier. Okay, this is what's happening. Okay, let me just clear that board for you. I've tried to draw the line y equals x there. I don't know if you can see it. It doesn't come out very well, does it? Okay, but the trouble is the line y equals x is a gradient of 1. Okay, it looks like that when you've got the graph plotted in degrees from 0 to 360 degrees. Or if you want, if you zoom in on the graph, okay, I've zoomed in. This is the graph of sine x. There we go. Look, it takes ages to get up to its maximum height of 90 degrees. Okay, so from 0 to 2 degrees, this is what sine x looks like. That's the graph y equals x. Can you see? There's no way the gradient of that is 1, is it? That's something completely different. Okay, it's not 1. In fact, the gradient is pi over 180 degrees of cosine x. Okay, but what that tells us is that if we differentiate, find the gradient using degrees, we get something that's not as simple to work with. The pi over 180 degrees makes it less easy for us to work with. Okay, and so for that reason, if I go back to the radians one, this result is a lot simpler. Okay, and that's really the reason why we use radians instead of degrees. Just simpler to work with, makes life much easier for us. We get nice simple results like the derivative of sine x is cosine x, derivative of cosine x is negative sine x. Okay, and it works for integration as well, of course. When you're integrating, okay, you get nice simple values. Okay, I'm hoping that you found that useful. Okay, I hope that was useful to you, and I hope you know a little bit more about radians now. I'll see you again.